All right, guys. In this video, I'm just going over the Unit 1 practice test that you were given. Now, this is just a quick little practice test. It's kind of going through the different skills you'll need. There's a few things that are missing that are on the other review packet, like being able to calculate percent error and that kind of thing. So don't forget about that stuff. But that's on your checklist, and that's on the other practice problems packet. I just want to take some time and go through the answers to this practice test. The key is, all right, so the key is posted, so you can just look at the key, but I just wanted to make a video to kind of maybe just explain some things. So if you're looking at the answers on the key and you don't know why that's the right answer, this is just going to give you a little bit more of an explanation to the answers. So, it's not everything. I would go back and watch. If you're struggling with sig figs, go back and watch the helpful videos on sig figs. If you're struggling with dimensional analysis, go back and watch the helpful videos on dimensional analysis, okay? If you're struggling with the metric system, then go back and watch the videos on the metric system. So just those little things. But here, and again, this isn't everything, but if you understand all of these different things in Unit 1, you'll be good for the Unit 1 test. And you might not get 100% because there's other things you have to know as well, but for the most part, you should do well if you get all this stuff. All right, so number one, just looking at a number and determining significant figures. So remember just kind of the rules. If any non-zero digits are significant, and then you really just have to focus on the zeros. Leading zeros never, captive zeros or sandwich zeros always, and then trailing zeros are significant if you actually see the decimal point written in the number, and they're not significant if you do not see the decimal point. You know where the decimal point is, you just don't actually visually see it on your piece of paper, then a trailing zero is not significant. If you do see it, then a trailing zero is significant. And that's it, okay? So 4 and 7, obviously, and that 0 is a captive zero, so it's significant. So this number has 3 sig digs, all right? Here we got 1 and the 9, so those two are definitely significant. And then we have zeros. Now these would be classified as trailing zeros. They did not write the decimal point. So those zeros, those trailing zeros are not significant. So that's why this one only is 2 sig digs. If we go over here to C, this is 3 sig digs. Why? Because these zeros would be considered leading zeros, and leading zeros are never significant. So it's just the 5, 4, and the 6. Those are your 3 significant figures there. Okay, if we go over here, these zeros again are leading zeros, not significant. This 0 is a trailing zero. And the reason why this 0 is significant is because I actually see the decimal point, okay, where we didn't see it over here. We know where the decimal point is, they just didn't write it. So over here, those trailing zeros not significant, but over here, this trailing 0 is significant. So that's why this number has 4 significant digits, okay? Then if we go over here, leading 0 not significant, okay, this 0 would be significant because it's captive or sandwiched, and then these 2 zeros at the end would also be significant because they're trailing zeros and I have eyes on the decimal point, okay? So that's why this number has 1, 2, 3, 4, 5 significant digits. Then if we look over here, right, this number is in scientific notation. It doesn't change anything. We don't have to take it out of scientific notation and put it into standard notation. If we wanted to do that, we'd have to move this decimal point to the right 31 times and fill in all the zeros in between there. And I don't want to do that. So if you have a number in scientific notation, whatever is typed in front of it, whatever is written in front of it there is a significant digit, right? So 1, 2, 3, 4, 5 significant digits. That's it. Okay. If I wanted to make it 6, I would add another 0 right here. Right? If I wanted to make it 7 sig digs, I would add another 0. If I wanted to make it only have 3 sig figs, I would take away these 2 zeros, and then it would just be 8.51 times 10 to the 31st. Okay. But the way this number as written, it has 5 significant figures. Okay. All right. So for scientific notation, remember, this tells you exactly what to do, right? It's in scientific, if a number's in scientific notation, it's take this number and multiply it by 10 7 times. Now, another way to interpret that is when you multiply by 10, you move the decimal to the right once. So this is multiplied by 10 7 times, so move the decimal place to the right 7 times. So the decimal here, we go 1, 2, and then it would be 5 more spaces because we already moved it 2 spaces, and that's how we get this number. So the decimal point was here, 1, 2, 3, 4, 5, 6, 7 spaces to the right. Okay. Now I'm not going to write the decimal point here because if I wrote the decimal point right there, it would make all these zeros significant. And when you're going from one type of notation to another, standard to scientific, scientific to standard, you want to maintain your sig figs. So this number has 3 sig figs, and then when I express it in standard notation, I want to try to maintain that exact number of sig digs, so 3 sig digs here. So if I put the decimal point there, now all those zeros there are significant, and I don't want that, okay? But what if it says 10 to the negative 2? Well, one way to think of it is take this number and multiply it by 1 over 10, 1/10, but do it twice. So 10 to the negative 1 is really 1 over 10. 10 to the negative 2 is 1 over 10 times 1 over 10. 10 to the negative 3 is 1 over 10 times 1 over 10 times 1 over 10, right? So if it's a negative exponent in your scientific notation, instead of multiplying by 10 that many times, you're dividing by 10 that many times. But when you divide by 10, instead of moving the decimal place to the right, you're moving the decimal place to the left that many times. So really what I'm doing is I'm taking this decimal point, and to put it in standard notation, I'm going to move it to the left because it's a negative sign, and I'm going to move it to the left 2 times because it's raised to the negative 2. So 1 space, 2 space. Okay. Now, technically, you don't need to put that 0 there. It's just, a lot of times that's how we would write it. But it's not significant, right? It's a leading 0, and leading zeros are never significant. So this number in standard notation still has 4 sig digs, just like our number started with 4 sig digs. Okay. And then here, so now we're going to take our decimal point and move it to the left 6 times. So we were here 1, 2, 3, 4, 5, 6. So that's our new number. Okay. Now going back the other way, just remember if the number's in standard notation and it's greater than 1, you're going to have a positive exponent here. If the number in standard notation is less than 1, you'll have a negative exponent. And it's really just how many spaces. Now remember, proper scientific notation has only one non-zero digit to the left of the decimal point. So technically, you could move the decimal points starting here, you could move it over 1, 2, 3 spaces, and that would be 491 times 10 to the third. And 491 times 10 to the third is correct mathematically. It's just not correct in terms of proper notation. We really want to keep moving the decimal all the way until we only have one non-zero digit to the left. And so we're going to say 4.91, and since it was 5 spaces, that would be times 10 to the fifth. But mathematically, there's no difference between 4.91 times 10 to the fifth and 491 times 10 to the third. They are the same thing. It's just proper scientific notation versus improper scientific notation. Okay. So here we're moving it to the left, and we're moving it to the left 8 times. So that's why it's 10 to the 8th. Okay. And over here we're moving it to the right, and we're moving it to the right 3 times. So we're going to use, when we move it to the right, and it's a number less than 1, we're going to make it, in scientific notation, it's going to have a negative exponent. And since we have to move it 3 spaces to get it right there, it's to the negative third. Okay, negative 3. Okay? So hopefully that makes sense. Okay? So here we're doing some conversions. Okay? So I'm going to tell you what to do mathematically. You could, if I ask you to do conversion and I don't express that you have to show your work using dimensional analysis, you could use the metric system number line. You could use, basically, you could use any way you know how to do a metric conversion. You really should focus on dimensional analysis. Let's just make sure we understand something. Like, I'm never going to have deca on a test. I'm never going to have hecto on a test or a quiz. This is just for practice. Okay, so, you should really mainly focus on, Mega, probably the biggest one, and then down to nano for the smallest one. But anyway, so milli to centi, you really just divide by 10, okay? Because there's 10 milliliters in 1 centiliter. But that's not an equality that you probably remember or memorize. But if you know there's 1,000 milliliters in 1 liter, so if we take this and divide it by 1,000, that'll give us to liters. And then if we know there's 100 centiliters in 1 liter, then we would multiply by 100. So we're dividing by 1,000, but then we're multiplying by 100. Multiplying by 100 and dividing by 1,000 is the same thing as just dividing by 10. So that's mathematically what it would be here, okay? Remember, deca means 10, not 1/10. Deci, lowercase d, means 1/10. This deca here, and technically deca is really DA, but we'll just say capital D means deca for this purpose. So deca means 10, all right? So to go from the base unit to tens of the base unit, we're gonna just divide by 10, so that many decaliters is equal to that many liters, okay? And then I'll do this one again because hecto is really not one that we're gonna see a lot in chemistry, never. So hecto means 100. So you have 6.03 times 100 grams equals how many milligrams? So we're going from hecto to the base unit, grams, and then the base unit to the millunit. So to go from hecto to the base unit, we multiply by 100 because there's 100 grams for 1 hectogram. And then from the base unit, grams, to milligrams, we multiply by 1,000 because there's 1,000 milligrams in 1 gram. So we'll multiply by 100 and then we'll multiply by 1,000. Multiplying by 100 is multiplying by 10 to the second. Multiplying by 1,000 is multiplying by 10 to the third. So you're really doing 10 to the second times 10 to the third, which is really 10 to the fifth. So really we're just moving this to the right 5 spaces. And that's how we get that. But again, you get a calculator, you can do all that stuff. Okay. All right, so the base unit. Notice it says base unit. So it's not asking for the SI unit, okay? It's asking for the base unit for the SI units. So remember, technically the SI unit for mass is kilogram, but if we want the base unit for mass, it's gram, okay? Everything else is a base unit. The SI unit is the base unit. So the SI unit for volume is liter. The SI unit for length, distance is meter. And the SI unit for time is seconds. So remember, temperature is Kelvin, energy is joule, amount of substance is mole. So make sure you go back and review your SI units. But it's just memorization. Okay. So here in section 4, we got some dimensional analysis. Okay. So this would be the setup, and again, here we're converting minutes to weeks. So we have to know these equalities. But when we get to part B, you'll notice that we were given equalities to use. But like you should know how many minutes are in an hour, how many hours are in a day, how many days are in a week. Okay. So we're taking our minutes. We know that 60 minutes equals 1 hour. So we're going to put 1 hour on top and 60 minutes on the bottom to get minutes to cancel out. Then we know 24 hours equals 1 day. So to cancel out hours, I'm going to put the 24 hour on the bottom and 1 day on the top. And then to cancel out days, I'm going to put 7 days on the bottom and 1 week on the top. And so if I just take 10.3 divided by 60, divided by 24, divided by 7, I end up with my weeks. I rounded to 3 sig digs because we started with 3 sig digs. We're going to assume that these are exact, even though they're maybe not exactly exact, right? There's 365 days in the year. It's really not 365. It's a little bit more like 365.25, right? So like, remember, metric equalities are exact, so metric equalities aren't going to limit you in terms of sig digs. If you wanted to say it's not exactly 7 days in 1 week or something like that, then you could say this is 1 sig dig, and then you could round this to 1 sig dig and just say 1 times 10 to the negative third if you wanted to. you can make that argument, but let's just go with, I started with 3, so I'm just going to finish with 3 here for that one. Okay. So we need 1,000 green beans, and we're told that we have 6 black beans in the jar, but we're told that 1 black bean equals 5 blue beans, 3 blue beans equals 4 red beans, and 1 red bean equals 10 green beans. And we want to know, if we have 6 black beans, how many green beans is that equal to? So again, we're just going to start with what we have, 6 black beans. And then I would use this equality to convert black to blue. The way it would work is I would put the 5 blue on top and the 1 black on bottom, because again, I'm trying to cancel out black and get to blue. Okay. Then I would use this equality that again was given to me in the word problem to convert blue to red. So since I have blue on top, I'm going to put this part of the equality on the bottom and this part of the equality on the top. This ensures that blue cancels out, and then I'm left with red. And then I'll use this equality to cancel out red and get to green. And so that would be the setup. Mathematically, it would be, remember, multiply by the numbers on the top, divide by the numbers on the bottom. If it's a 1, you can kind of skip that step because multiplying by 1, divided by 1 doesn't do anything. But it would be 6 times 5 times 4 divided by 3 times 10, right? And it doesn't have to be in that order, right? PEMDAS. You could do multiplication and or division in any order you want. So you could do 6 times 5 times 4 times 10 divided by 1 divided by 3 divided by 1. You should get the same answer. Okay, so it comes out to be, you got 400 green beans. So 6 black beans is equivalent to 400 green beans. So you still don't have enough to get that class party. Okay, so here, 16.9 inches. You want to know how many yards that is. So we got to go back to how many feet are in a yard and how many inches are in a foot, or you could have done this in one step by knowing there's 36 inches in 1 yard. Okay, so I went from inches to feet first because I know that 1 foot equals 12 inches, right? So that's the equality I would be tapping into to convert inches to feet. So if I take inches and I divide by 12, that gives me feet. Okay, and then I know there's 3 feet or 3 feet in 1 yard. So if I divide by 3, that's going to cancel out feet and give me yards. And so 16.9 inches is equal to 0.469 yards. Okay, but right, understand mathematically, if you take 16.9, divide by 12, and divide by 3, it's the same thing as taking 16.9 and dividing by 36. Because what's 12 times 3? 36. So it's, mathematically it's the same thing. It just depends on what you know, right? Like, were you able to come up with that equality in your head? 36 inches equals 1 yard, and then you can make that conversion factor. But if not, inches in a foot, feet in a yard, hopefully. If you don't, yikes. Something to think about. But yeah, okay. So here is a mole conversion, but with the given information, you might be able to just do it in one step. So normally, if we have atoms of something and we want to convert it to mass, usually we're thinking on a mole map, we're going to go from atoms to moles. Okay, and the way you go from particles to moles is you divide by Avogadro's number. And then once we have moles, we're going to go from moles to grams by multiplying by the molar mass, and you can find the molar mass of the substance on the periodic table, right? But this is just taking 2 concepts and making it into one equality, 2 equalities and combining them into one. So the way to think about this, right, is that 1 mole of helium atoms is equal to Avogadro's number of helium atoms, and you also know that 1 mole of helium is equal to 4 grams. And you get that number 4 by looking at the periodic table, right? That's the molar mass, 4 grams per mole. But think of it as an equality. 4 grams of helium is equal to 1 mole of helium. So if 1 mole of helium is equal to 4 grams, and 1 mole of helium is equal to Avogadro's number of particles, that means Avogadro's number of particles of helium is equal to 4 grams of helium. So that would be an equality you could use. And so since we have atoms, we're going to put the atoms part of the equality on the bottom. And we want grams, we'll put the grams part of the equality on top. We'll cancel out our atoms and get grams. And what do? We take this number and multiply by the top and divide by the bottom, or take this number and divide by the bottom and multiply by the top, either way, okay? And we're doing exactly what the mole map said, right? To go from particles to moles, we divide by Avogadro's number, so we're taking our particles and we're dividing by Avogadro's number. But then to go to moles to grams, we multiply by the molar mass. And that's what we're doing with the molar mass on top here. Okay, so atoms will cancel out and you'll be left with grams of helium, or you can just say grams. And we're going to round to 3 sig digs because I'm going to say this is 4.00 grams. So I'm going to give the molar mass 3 sig digs, and Avogadro's number has 3 sig digs. And this has 4, so we got to limit it because of Avogadro's number and the molar mass. 4.00 only has 3 sig digs, so we got to limit it to 3. Okay. And then the last part, a beaker. A beaker does have graduations on it, but you can kind of estimate how much you have using a beaker, but you really never measure using a beaker. You want to use a graduated cylinder or a burette, okay? But you don't use a beaker to measure. A beaker is just for holding stuff, right? And most likely, liquids, okay? Remember, this one I could give you, either one, because technically Fairfax County doesn't want students to handle fire extinguishers. They don't really want the teachers to handle fire extinguishers. Fairfax County's policy is, hey, if there's something going on in the laboratory classroom where a fire extinguisher would be required, instead of doing that, everyone should leave. You should pull the fire alarm so the entire school evacuates, and the fire department is going to come and let the professionals use the fire extinguisher. So that's the technical county policy. But understand something, right? Maybe you're going to be in a lab somewhere, or maybe you're at your house and you're like, should I use the fire extinguisher on that fire? Well, just remember, unless it's the only thing you have to put somebody out, you really don't want to spray anybody with a fire extinguisher. So don't spray people that are on fire with a fire extinguisher, unless it's maybe your only option, okay? You don't want to do it. It's loaded with CO2, it's loaded with other chemicals that can be hazardous if you inhale them. So it's really not the healthiest thing to do, okay? So really, the distinction is, remember, the fire blanket is for when someone is on fire, smother them, wrap them up in a fire blanket and put the fire out that way. But if the lab were on fire, you could use a fire extinguisher. So when something is on fire, fire extinguisher. When someone is on fire, fire blanket. But again, if somebody at home is on fire, don't spray them with a fire extinguisher. Try to extinguish the fire by smothering it with a blanket or something, okay, if you can. But if, your stove's on fire, go ahead, and you got a fire extinguisher, go ahead and use the fire extinguisher for that, okay? And then remember, neutralization, that's a type of reaction. We kind of talked about it in class a little bit. We'll study it a lot more later on this year. But it's what acids and bases do to each other. Acids neutralize bases, bases neutralize acids. We're going to talk about all the chemistry behind that. But right now you just need to know acids neutralize a base and base neutralize an acid. So if you spill a base on your desk, before you clean it up, pour an acid on there to neutralize it. If you spill a base, if you spill an acid on your desk, put a base on it to neutralize it. If you spill a base on your desk, put an acid on it to neutralize it. And just remember, vinegar is what we have in the lab to neutralize bases. Vinegar is an acid, so if we spill a base, we'll put a little vinegar on it to neutralize it before we clean it up. And then baking soda is what we have in the lab to neutralize an acid. Baking soda is a base, so sodium bicarbonate is a base. And so if you spill some acid on your desk, you're going to pour some baking soda on it to neutralize it before you clean it up, okay? And yeah, that's about it. So hopefully that helps clears things up if you were looking at the key and you weren't understanding some of the answers. But yeah, good luck and happy studying.